Okay, so elimination reactions. You've heard of E2, which is the concerted version, where the rate, the appearance of elimination product, is equal to some rate constant times the concentration of your alkyl halide or something with a leaving group and the concentration of your base. You've also heard of the E1 reaction, in which the rate depends only on the concentration of your alkyl halide or whatever alkyl group plus a leaving group, and not on the concentration or identity of the base. But there's another extreme that we ought to consider, and that's called E1CB. And this has more complicated kinetics. So I'm not going to write out that rate law. But the rate determining step in many cases for E1CB involves only one thing. And so the rate law, depending on how you write it, will only involve either the alkyl halide or the base, depending on which group is the which step is the rate determining step. An example of an E1CB mechanism is this. Suppose you have a molecule with a leaving group here. Here's the alpha carbon. Oh, no, that's not what I wanted. Alpha carbon, here's the beta carbon, here's a proton that we would remove, and then attached to that beta carbon is an electron withdrawing group. In such cases, it's possible for a base, we'll, for this specific example, use a tertiary amine, to remove the proton from the carbon that is beta to the leaving group to give you an enolate intermediate, and this gives you a sense for why this can happen, because the conjugate base is stabilized by resonance. And then in a second step, electrons from that beta carbon can kick down and kick off the leaving group. And then you end up with your eliminated product. Oh, sorry, that's yuck. Why am I struggling with this? Leaving group left, yeah, there's the double bond. Okay. So you've got a rate constant here, a reverse rate constant there, and another rate constant there for the actual elimination. So let's think about the possibilities for rate laws for this E1CB mechanism. And we're going to use the term E1CB as a sort of catch-all term for elimination reactions that are stepwise, where deprotonation happens first. Technically, the fact that it says E1 and CB means that would mean that the rate determining step is elimination, K2, and it only involves the conjugate base and not the base. But there's a continuum, as you can imagine, of mechanisms. And we can write a rate law that accounts for all of those possibilities by doing the steady state approximation on the conjugate base. That is, we're going to say that its concentration doesn't change over the course of the reaction, and we'll set the rate of change of this conjugate base intermediate equal to 0 and follow that through. And if you do that, you come up with the following expression, and we don't need to derive that now. You can go back and convince yourself that this is the case. K1 and K2 times the concentration of the leaving group times the concentration of your base divided by the reverse rate times the concentration of the conjugate acid of your base plus K2. All right, and again, you would have gotten this by setting the rate of change of this molecule's concentration equal to 0, taking into account the forward rate that comes from K1 and these two molecules, the reverse rate, which comes from K minus 1 and this intermediate, and then the forward rate K2, which is K2 times this intermediate. All right, questions so far? So let's think of some limiting cases. What if, and this is what most people think of when they hear E1CB. Let's imagine that deprotonation is fast. And that K minus 1, backwards deprotonation, is faster than K2. In other words, if we call this step 1 and step 2 is rate limiting. All right, how does that change things? If the K minus 1 term is much larger than the K2 term, then we simplify the rate law by leaving out the K2 term in the denominator. Oops. Okay. And then if we think about the equilibrium between acid and the base and its conjugate acid, we might say that Ka for the conjugate acid is equal to H3O plus times B minus divided by BH. Or alternatively, Ka divided by H3O plus equals B minus divided by BH. So we could rewrite this equilibrium in terms of Ka times K1 times K2 divided by K minus 1 times the concentration of your starting material divided by the concentration of hydronium. And so you would see here that the rate is independent of base concentration provided that you keep the pH constant. So if you did this reaction in a buffer, because this is a fast pre-equilibrium, this is an example of specific acid or specific base type of catalysis, in the sense that the proton removal step happens before the rate determining step, and therefore it doesn't matter how much base you have present as long as you control what the pH is. Either of these expressions is fine, but this is just pointing out that if you do this in some kind of buffer where you can control the pH, it no longer matters how much base you have, just what the pH is, because that will allow you to balance the equilibrium between these two species. Okay, so that's example 1. And notice that if you keep the pH constant, all of this would collapse to some K obs times the concentration of your starting material. So that's why it's called an E1 type reaction, because provided you keep the pH constant, the only thing that's changing there is the concentration of your starting material. Everything else, every other term, is a constant. All right. So I would say that's case number one. That is sort of the classic E1CB mechanism. Anything you want to say about that? Any questions? All right. So case number two might be that actually step one is irreversible and rate limiting because K2 is so fast. Okay, so an example of this would be, say, a molecule like this. And the pKa of this proton that's alpha to the carbonyl and beta to your cruddy leaving group is in the 20s, whereas the pKa of methanol is like 16. So there's not very much enolate. I'll draw this resonance structure of the enolate. Not very much of that forms. There's an equilibrium here, K1, K minus 1, and then K2 to give you the elimination product and your leaving group. All right. So in this case, if we say that K2 is much, much faster than K minus 1, if we go back and copy our rate law based on the steady state approximation, if K2 is now much, much greater than K minus 1, then all of this simplifies to K1, K2, starting material, base concentration, divided by K2. K2 cancels out, and we end up with something that looks very much like an E2 rate law. All right. In this case, because the first step is rate limiting and the second step is fast, your expression for the rate law is going to contain terms for both the base and the starting material. And this would look in form very much like an E2 reaction. But there's a key. And that is that because the rate determining step does not involve the leaving group, changing the leaving group shouldn't cause much of a change in the rate. And so people have done Hammond analyses to try to pin this down. An example of such a case would be where we have this benzoate leaving group where we're going to put various X groups there to attenuate the electron density on the benzoic acid conjugate base that leaves. If the first step is slow, to give you the enolate intermediate, and I'll just draw one of the resonance structures of the enolate. And then the second step, which is elimination, is fast, where your leaving group is this benzoic acid with the X group here. If this were the rate determining step, if leaving group leaving were the rate determining step, then you would expect groups that stabilize the conjugate base of benzoic acid, groups that stabilize the negative charge on that leaving group, to accelerate the reaction. But in fact, for for reactions where step 1 is rate limiting, making the leaving group better doesn't make much of a difference. And you would observe this by, if you did a sort of k-obs or log of k-obs versus sigma, you would see a rho value less than 1, probably close to the less than 1, probably greater than 0, indicating that it's not as sensitive as benzoic acid deprotonation is. All right. So sometimes people will, I've never seen this before, but your text mentions it, so we'll mention it here. People will call this scenario E1CB IRR to indicate that the first step is irreversible. You can promptly forget that. I don't care about it at all, but if you see that, you'll know sort of what they're talking about. All right, so we now have 3 sort of mechanisms that we can consider for elimination reactions. And what we're going to do is make one of those Moore or O'Farrell-Jenks plots, which we hate, but which can be useful in helping us consider reaction mechanisms. So remember, this is a reaction coordinate energy diagram that's three-dimensional really, and we're only showing 2 dimensions of it. We're going to have one reaction coordinate on this x-axis, another on the y-axis, and then energy will be coming out of the page at us, and we'll just have to imagine that because we're not going to draw energy levels. So in the upper right-hand corner are going to be our starting materials for an elimination reaction, which are, of course, going to be your alkyl halide or whatever type of leaving group you have. And you've got the alpha carbon here and the beta carbon there. And then you're also going to have a base. Now, let's let the y-axis be extent of leaving group departure, and then the x-axis can be extent of deprotonation. So if we just only move down the y-axis, I'm sorry, penmanship is so cruddy. I'm going to try that again. Not sure this is an improvement. All right, if we simply move down the y-axis, that would be the leaving group leaves before the beta proton has been removed and before the base has, before the base has removed the beta proton. This would be a carbo-cationic intermediate. And this would be sort of what we would expect for an E1 reaction. And then, of course, after that, the base could come in and remove the proton. You would establish a double bond between the alpha and the beta carbons. The base will have picked up the proton. So if we go on the orange pathway where we deprotonate first, where we have leaving group leave first and then we deprotonate, that is the E1 pathway. Similar to the way when we did Sn1, having the leaving group leave first and then the substitution reaction described the Sn1 pathway. If we have the leaving group leave at about the same time as the base removes the proton, that would be a path straight across the middle, and that would be sort of the concerted E2 pathway, right? And there would be some transition state there where the leaving group will have partially left and the proton will be partially removed. Finally, and this was a corner that we didn't consider much with the Sn1 reaction, but now we can for the elimination reaction. This is where the proton gets removed first. To give you an anion on the beta carbon, and then in a second step, the leaving group leaves. And so, got to choose maybe purple, and this would be your conjugate base intermediate. And then after you deprotonate, the leaving group leaves, and this would be the E1CB pathway. Okay. Making sense so far? Do you see these three extremes? We don't really have this sort of extreme for the SN2 reaction because for substitution reactions, because carbon's not big enough to really have 5 things bonded to it. All right. But here, since we're just removing a proton instead of doing a substitution reaction, that extreme is a possibility. So let's just use this diagram to talk about things that might bias the equilibrium towards one of these things or another. All right. Let's see. Let's first consider what having a stronger base would do. All right, so let's examine the effect of okay, so I want you to look at this diagram and tell me in terms of energy, that is the z-axis coming out of the page or going down below the page. And I've got these 4 corners, we'll call them A, B, C, and D. If I make the base stronger, which corners is that going to affect, and which way are they going to move, higher in energy or lower in energy? All right, so take a look at that. If I make the base stronger, which corners will be affected and in what way? A will be affected because the base is there, good. It should go up in energy, right? It should come up out of the page. So maybe we'll put a little bit of an arrow in pink for this corner moves up if we make the base stronger. Okay, anything else should be affected? Okay, we'll talk about how that's going to affect the transition state of the E2, absolutely. But first, let's deal with the corners. Are there any other corners that are affected by the base? C should be as well, because the base is there too. So that should also raise the energy of C. Okay, now, this is just a review of these diagrams. Remember, for corners A and D, if you raise corner A, making the starting material higher in energy, that takes this transition state and pulls it towards A, makes the transition state earlier. That's called a Hammond Effect. Okay, so we'll draw a dotted line arrow here indicating that we've the effect of moving A upward is maybe I'll put a little A by it so that we can see that's the effect of raising the A corner. Now, for corners B and C, these function very much, these affect the transition state for the E2 reaction very much like you would expect a marble rolling on a sheet. That is, if I raise C, that's going to cause the transition state to move away from C and towards B. Okay, so the effect of raising C on this transition state. We'll put a dotted line here. Sorry, and it's got to be more or less perpendicular to that diagonal. That's the effect of raising C. Now, put those together, think about vector math, and what have you got? Well, the addition of those two is probably to move the transition state here. Okay? So this is the new E2 transition state. So if we use a stronger base, what does that do to us? And let's sort of compare where we were before versus where we are now. Prior to that change, the transition state had this much deprotonation and this much leaving group departure. If we raise both corners A and B, notice what that does. It actually doesn't change the extent of deprotonation. That stays the same. But instead, it lowers the extent of leaving group departure. So the impact of adding a stronger base is same amount of deprotonation in the transition state, but less leaving group leaving. And to some extent that makes sense. A stronger base won't need the leaving group to depart so much before it can remove this proton. Because remember, as the leaving group departs and we get a buildup of positive charge here, that lowers the pKa of the beta proton. And so if the base is stronger, we don't need such a lowering of the proton's pKa. All right, you follow through that reasoning? Okay, so let's talk about the other thing that people sort of think about when dealing with E2 reactions and whether it'll be E1 or E1CB or just E2. Let's talk about making a better leaving group. So I'm running out of colors to choose here, so I don't know what to do. Well, cyan, that's fun. Let's try cyan and make it a little bit thicker. So let's suppose we use a better leaving group. So let's look at the corners, and I guess so let's talk about what having a better leaving group should do to any of these corners. Which corners will be affected and why, and how? And just as a hint, remember good leaving groups are conjugate bases of strong acids because they can tolerate the negative charge. They're more stable once they've left. So, which corners will be affected and how? C and D, okay. And why do you say that?
D because the leaving group is there.
Okay, yep. And same with C, right?
Yeah, same with C.
Okay. So in which direction will they be affected? Should they be raised in energy or lowered?
The group is lower in energy because the leaving group is better. So
Yep.
it's more stable.
More stable leaving group, so let's put a blue arrow by the C and a blue arrow by the D. And let's consider what that will do. All right. So for A and D, we have to consider the Hammond effect, which says that if I raise the energy of A, that moves the transition state towards A. Similarly, if I lower the energy of D, that's going to make the transition state even more starting material-like. So we're going to draw another vector overlaid on this one for A. We'll call that lowering D. That will have that effect of making the transition state more, the Hammond effect, more closer to starting materials than to products. And that makes sense, again, according to the Hammond postulate, the transition state is most like whichever adjacent intermediate or starting material or product that it's closest in energy to. So if we make this product go lower in energy, the transition state's going to move earlier. Now we have, with C, we're lowering this corner. And again, for the off-diagonal corners, the effect is just what you would expect for a marble on a sheet. So if I lower C, I'm going to move the E2 transition state this way, sort of perpendicular. And oops, and that will be because of what we did to C. And overall, the net effect of that, if we add those vectors, is going to put the new E2 transition state here. Notice that it has the same extent of leaving group departure, but way less deprotonation. That's almost exactly the opposite of what you might have predicted just based on logic and reasoning, right? You might think, oh, a better leaving group, then in the transition state, the leaving group should be more gone. Well, actually, no. You have the same amount of leaving group departure, but less deprotonation. In other words, the leaving group is able to leave even more, is able to leave to the similar extent without a similar amount of deprotonation. Doesn't take as much deprotonation to get the leaving group to start to leave. And notice that as the transition state, I haven't drawn for you the pathway that would go through this transition state, but notice that it would be angled more towards the E1 extreme, right? And if we pushed it far enough, this would become an E1 reaction rather. Leaving group would leave first and then deprotonation would happen. Similarly, by making the base stronger, we have pushed the E2 reaction more in the direction of E1CB, where if we go all the way up here, then we are going to remove the proton first and then the leaving group leaves. Notice what it would mean if we had a transition state here. This would be the E1CB transition state, and this would involve a certain amount of deprotonation with zero leaving group departure, right? Whereas if we pushed this transition state here all the way over there, that would be this extent of leaving group departure without any deprotonation at all. So those are sort of how we can navigate between those extremes, and hopefully by now you're thinking of these reactions in terms of a continuum of possibilities rather than discrete options. There are other things we could talk about. We could talk about stabilizing the carbo-cationic intermediate and what that would do. We could, but I don't want to necessarily deal with that because I think you could handle the effect of that. Reason through that on your own. The last thing I want to do is including an electron withdrawing group on the beta carbon. So let's imagine what that would do. Let's add an electron withdrawing group here. And let's consider what that would do. And what effect that would have on our various corners. Okay? So, what do you think? Which corner would be most affected by the electron withdrawing group on the beta carbon?
Most affected in terms of
Energy. Putting an electron withdrawing group on this beta carbon should have the greatest impact in terms of energy on which of these corners?
to destabilize.
Would it destabilize C? I think so. Like you've got a positive charge and you're withdrawing electron density there, so probably there's an increase in energy for C. How about B? What do you think there? Electron withdrawing group adjacent to a negative charge. What should that do? Stabilize it versus not having that electron withdrawing group there. So probably adding an electron withdrawing group. Oh no. I'm abandoning our color scheme, which is making me upset. So we're going to simultaneously lower the energy of B and maybe increase the energy of C as well. Again, these off diagonal corners B and C have the effect of a sheet with a marble rolling around in it. If you lower this corner and raise this corner, the effect is going to be actually to do to move the transition state to that particular point. So this is the effect of lowering B and raising C. All right, what will that do to a transition state? Well, actually, that's one that affects both extent of deprotonation and extent of leaving group departure. So if we have a better leaving group, our transition state will have less leaving group departure, but more deprotonation. So of all the things we've talked about, biasing a reaction towards an E1CB mechanism appears to be most effectively done by introducing an electron withdrawing group on that beta carbon. Or by using a stronger base. Okay, so anything else you want to ask about that or talk through? Sorry, Stephanie, did you?
Yeah, it's because I don't understand why if you decrease B, it's going in the same direction as C. I understand when C.
Okay, so for the one in pink was we make
I'm talking about the red one.
right. We decrease B decreasing B has the same effect as increasing C. Right, think of a sheet of paper. This is B and this is C. If I raise C, that's going to push things towards B. Similarly, if I keep C the same but lower B, it's going to have the same effect as pushing things towards B. Still no?
No,
That's okay.
I can.
Let's work through it again. That's all right.
Yeah, it's because I was thinking the page. And
Uh-huh.
you see, the effect is going like in that direction. I understand that.
Okay.
But B, if you blow, because it's the opposite of B and C. Maybe I'm just confused.
Okay. One thing that is difficult to remember is that the effects on A and D are different from the effects with B and C. So focusing just on B and C, That's like you have a marble in the middle of a page and these are the corners, B and C. If I lower B, the marble's going to roll towards B. If I raise C, the marble's also going to roll towards B. So lowering B and raising C have the same effect. I'm sorry. Go ahead. Go ahead and ask a follow-up question because I'm not sure I'm explaining it well.
No, it's fine.
Okay. What else? Okay. Well, let's talk about acyl substitution, which is thought of as tandem elimination, tandem addition and elimination reactions. And one of the key issues to think about is the extent to which acid and base catalysis are needed. So a first example, have we done this already? We didn't do imines yet, did we? No? Okay. So a first example of substitution at sp2 hybridized carbons would be imine formation, where you have a ketone or an aldehyde and then some amine. And depending on the identity of the R group, we can have different outcomes and different stabilities of products. But for imine formation, the first step seems to be attack of the amine on the ketone to give this tetrahedral intermediate with a positive charge on the nitrogen. And it's thought that very quickly, it's thought that this step is slow, that very quickly gets deprotonated on the nitrogen and protonated on the oxygen to give you this sort of tetrahedral intermediate, which is called the carbonyl amine. All right, and then at this stage, this is where you need an acid catalyst. And you need the acid catalyst to protonate the OH group to turn it into a good leaving group so that the nitrogen can kick off that water as a leaving group. And this intermediate is called an iminium ion. And then in the final step, you have deprotonation of the iminium ion to give you your imine, and you regenerate your acid. Okay, so you sort of got step 1, step 2, step 3, and step 4. Though arguably, no, that's fine. I think we've got them all. Sometimes people will show this as more than one step. First, you remove this proton, and then you put a proton on the oxygen, or vice versa. So this may be 2 steps, but in either case, they're fast. All right. So imine formation has some interesting pH dependencies. So if you look at the rate of imine formation as a function of pH, it basically gets to a maximum around sort of pH 6 and 7. Much above that, the rate is very low. pH is higher, also much lower than that, the rate is slow. And the effective pH changes which of these, pH sort of changes which of these steps is rate limiting. So let's see. Below pH 4-ish, step 1 is rate limiting. slow. And the reason for that is because of the equilibrium between the amino group and H3O plus with the conjugate acid of the amino group, the ammonium, and H2O, right? And there's some Ka associated with that. And I may have it backwards, but in any case, the pH will determine how much of the amine is present versus the ammonium. And so if you get pH too low, you're not going to have enough amine present versus ammonium, and that's going to slow down this rate, which will depend on both the concentration of ketone and concentration of your amino group. In contrast, at higher pH, then step 3 is rate limiting. And the reason for this is that at higher pH, you may not have enough acid to protonate the OH to turn it into a good leaving group so that you can get to the iminium. If step 3 is rate limiting, then this is general acid catalysis. And the issue here again is, do you have enough acid to make step 3 faster? So the maximum rate is sort of the Goldilocks position where you have enough amine to attack so that step 1 is fast, and you have enough acid so that step 3 is fast. And it's nice that that happens to be around physiological pH, because imine chemistry is pretty important in biology. So we'll stop there and we'll pick it up next time. Stay tuned for your exam.